let's get going tonight. Welcome to Little Thompson Observatory. My name is Micah, one of the volunteers here. We've got a whole bunch of volunteers standing along the sides, so if you guys have any questions, ask them about what's going on here and what about. How many people are here for the first time in the observatory? Wow, quite a few. Okay, let me give you a 2-minute introduction as to what we do at the observatory, how we got here, and then we'll introduce John, our speaker for tonight. And he promises that we won't talk very long, but
what?
I think it will go for an hour to an hour and a half. How about a little break after an hour? Is there a breaking point somewhere in your
break at an hour.
In your little dissertation here?
Yes.
Good. Okay, Little Thompson Observatory, 1996. We got word that we could get a telescope donated through Mount Wilson Observatory from a program called Telescopes in Education that ran at Mount Wilson Observatory in Pasadena. And the only requirement was to put it in a public facility, so we formed Little Thompson Science Foundation, a nonprofit, fundraised a little bit of money, and built this facility in 1998 and 1999, opened it middle of 1999, expanded it to house a second telescope behind this wall in 2005, and currently we are expecting our 50,000th visitor by the end of this year. So for a little worth it, we've done pretty interesting stuff here. We're not nerdy astronomers. If anybody came here with the idea of seeing nerdy astronomers here, you won't find them here. We're more an educational organization that likes to get students K through 12, our primary audience, educated and not to be afraid or intimidated by physics, by math, by science, all the tough stuff in school. And we're doing that with astronomy as a teaching tool, basically. So that's why we're not on top of a mountain, way far away from everybody. That's why we're right next to the football field. We're even open when they have a home game, as you can see, right? So if you don't like this talk, no, I wouldn't say it. The interesting thing is that it must be in their genes that the jocks never come in here. We've tried and tried, but we've never seen a jock in here. So. Anyway, so that's kind of what we do. We run with an all-volunteer staff here. We're open any day or night of the year if there is an appointment. We are open by appointments. So you can go to our website, starkids.org, make your own appointment, pick a date that's not taken already, and schedule your group in here. We'll put 1 or 2 volunteers in here to help you. And it's your evening, so you tell us what you want. You want to learn a little bit about astronomy, you want to look through the telescope, you want to go see some stuff, some specific stuff, and a volunteer will try to do that with you. There's no charge for what we do, except we certainly take donations. We're running off donations and grants, basically. We're not related to the school, because we're on school grounds, but the school has a magnet astronomy class in here every Thursday night. So Thursday nights are usually not a good night to schedule, because the school has the facility and they're using that for the class. If you give us a donation, we have certain small trinkets in return for the donation. We have t-shirts. Right now we're trying to get rid of our t-shirts. T-shirts have the old design on it.
There it goes.
Single dome. We now have a 2-dome facility.
See good. There you go, man.
Only one thing, you get collector's items. So for anybody who's so kind to give us a donation, please don't leave it out.
Yes.
T-shirt, cup.
Give us a donation and demand a t-shirt.
Demand it.
We also have mugs, we have bookmarks, all that good stuff. We have some Galileo scopes behind John there. We have some 2-inch Galileo scopes still that we, for a $30 donation, you can get one of those. It's the same telescope. Yes, sir?
Is anybody a little warm in here right now?
Yes.
Yes.
Okay.
No, not me. I just, John had mentioned it. So Since we have the doors closed for the mosquitoes.
Okay, we'll put the cooler on. So anyway, if you give us a donation, demand something in return. See John. John is really good at that, giving away stuff. So, let's see, what else did I not talk about? Oh, the second telescope we have here, we'll take you up there. It's not running yet. You've heard me say that all year. It's not running yet. We're still working on getting the dome automated. But that was the NASA Apollo space program telescope that investigated whether the moon had a solid surface or had a very thick dust layer. NASA didn't want to lose the astronauts on the first mission to the moon, right? They disappeared. So they picked the landing spots with the telescope after they figured it was pretty safe to land on there. And so we can show you that telescope. It's a 24-inch primary mirror, so it's a pretty big telescope that we have. The one on that side that we're using tonight is an 18-inch Tinsley telescope. It's a very nice instrument. And piggybacked on that is a 6-inch astrophysics refractor that Professor Johnson donated. Thank you very much again. And so he moved to Colorado from New York, the state of New York, and now he can still build a telescope here. Good stuff. Any questions as to what we do? If you want to sign up as a volunteer, go on our website, starkids.org, and sign up as a volunteer. We'll put you on our mailing list. We'll teach you how to talk to audiences, how to read the star walls that we have, and how to operate a telescope. And as a good benefit of that, you can use the telescope after the groups are gone. So you don't have to buy your own big telescope. You can use ours. So any enticement we can do. Okay, after this little introduction, let me introduce John. John became a volunteer about a year ago when he moved from Greenbelt, Maryland, or Washington, D.C. area, roughly to Longmont. John is a scientist that works with NASA and reviews basically all NASA's educational materials for appropriate level and stuff like that. He's a real
Subject accuracy.
Subject accuracy and all that stuff. And he has done a couple presentations for us. What we had asked him to do is to do a little deeper presentation, and he says I got to do that in 2 segments. So last month we had segment 1 of 2 of the theories of everything: relative theory of relativity, gravity, electromagnetic force, what have you. So tonight he's going to talk about the second part of his installment. After an hour, hopefully we'll get a little break.
Mark the time.
Yes, mark the time. If people are not interested anymore, I mean, come see me and I'll take you up with a telescope and we can go look through the telescope. If you guys get bored, I mean, it doesn't matter. This is tough material. But hopefully everybody will like it. John encourages a lot of questions during his, so don't try to save until the end because you forget it. I can promise. He will go through 2,000 years worth of theory probably. Right?
That's all.
Yeah. In about an hour and a half. Yes, sir.
So how many theories of everything are there?
We are playing with a total of 3 major ones, but that's probably where 2 of them is where all the money's going, and the 3rd one is an outlier, but you'll see why I cover it.
Ask as many questions as you want and enjoy the evening. Thank you.
Thank you.
Need some pacing space here. All right. Well, hi everybody. I saw a bunch of hands who are brand new to the observatory. How many people also were not here last week? Month. Feels like a week. So, all right. So the first about 15, 20 minutes here will be a quick recap of the top points there, and these are the important points that we need for the rest of tonight. So I'll get going here. We did have a question from last time. That someone asked we talked a little bit about CERN and the Large Hadron Collider, and they asked me what the 4 major instruments do there. And to confess, hold on a second.
Sorry.
Well,
you didn't say push that out.
That's right. You just said push the red.
well, it should have been.
How many volunteers does it take to run a video?
Obviously not
There we
enough.
go.
You should see us install a swamp cooler.
Yeah. People who can't be here and they're saying, oh, please record it so I can see it. So we're doing that. So now you can hit record. Yeah. Go ahead and hit the red button. Alright, so, yeah, to confess, I'm more interested in the science that comes out of all the cool instruments and projects we do and how it all fits together than the cool instruments and projects themselves, which is strange. I mean, I'm interested in what they do, but kind of like what the findings are. So I had to look these up, and one of them is the Atlas is a general purpose detector, looks for signs of new physics, origins of mass, extra dimensions. CMS is looking for the Higgs boson, and we talked about that last time. That's one of the last missing pieces of being a last missing piece in what's called the standard model of quantum physics. And we haven't found it yet, but we're narrowing in on it, finding regions of energies that we don't have. So they're looking for that hard. And what that, the field that that is part of, we believe gives everything mass. So that's the reason we're looking for that. Alice looks at fluid forms of matter, so really high energy stuff. The things deep inside of even protons can start to act like strange fluids, and so they're looking at that. And the LHCb looks for one of the problems that we have is why do we have a bunch of matter around us and not antimatter? Or why weren't they both equally created in the beginning and then nobody would be here to talk about it? So that's just a little bit of cleanup from last time's questions. Where we started was way back in time about how mankind likes to make theories of everything. And so going all the way back to Aristotle, we have the idea of crystalline spheres around the Earth, and the last sphere has holes in it that let the light of heaven through, and those are the stars. And so these unifying ideas, it didn't really involve forces or anything, but it was good enough to last about 2,000 years. It kept everybody who cared about those things happy. But what we're looking for are the four forces: electromagnetism, gravity, which are very comfortable with gravity. Physicists aren't, but you are. And the strong and weak nuclear force, which are important deep inside the atom for keeping the nucleus of the atom together, and also responsible for radioactivity. The weak nuclear force helps with that, among other weird things that go on in there. So since gravity, even though it is a problem child, because it's really, really weak compared to everything else, you're used to gravity because you fall off a chair and you hurt your knee. So I spent most of the time talking about attempts around gravity. And the first big unifying shot we got with gravity was Newton. And he actually penned down an equation that you could predict things from. You could plug in numbers and say, all right, we have a planet over here, and a planet over here, a star here, and a planet here. How are they going to interact with each other through gravity? And it was a pretty simple little equation, and it's good enough to get spacecraft out into the solar system and to other planets. And yeah, Einstein came along with and came up with a more refined version of this, but we don't really need to use it very often. We do with GPS devices, but this is good enough still, so many years later. So Einstein did come along, and he had a question as a teenager saying, if I have a light in front of a train, and the train speeds up to the speed of light, what do I see when that happens? And think about it, this is coming out at the speed of light. If I'm going the speed of light, then maybe the light gets sluggish and kind of cools up and makes a little cloud in front of the headlight. Maybe? No, it doesn't. What he found out is that speed of light is the speed of light no matter what. Speed of light is a constant, no matter what you're doing. So something has to give, though. So what gives is space and time itself. So in this attempt to work out that simple problem, he came up with special relativity, which says time slows down and space shrinks as I approach the speed of light. So I'm running along like this with my flashlight, and what's happening with my, from my point of view, is world, the universe around me seems to be running at a different rate. People looking at me see me going slower and slower and slower. My heartbeat goes slower, my clock's running slower, I talk slower. It really is. It's not just a observation effect. It really is happening. When I hop off and come back home, I will be a lot younger than the people I left back at home. So in a way, you get to travel into the future a little bit, because everyone around you will be there 10 years older if you go long enough and fast enough. People watching me will also see that I get skinnier in the direction that I'm moving. And near the speed of light, my entire spaceship would be down to a thin little line. So really strange stuff, but we use that all the time in particle accelerators and things like that, like at CERN. And we see the particles that we accelerate last a lot longer and gives us time to see what's going on in these collisions that are happening inside those devices. General relativity came next, took him some more work to do, but this brings in gravity. Remember, we're looking at gravity first. And here he found out that time slows and space shrinks or warps in very high gravity. And I don't know why that's twice up there, but so as I just standing here happy on the surface of the Earth, my clocks are running a little slower, your clocks are running a little slower than a clock out in space between the Earth and the Moon or between the planets or further. And it matters enough that the little GPS devices that you have in almost every smartphone would be off, completely useless within a few hours or days if they didn't have the equations of general relativity in there. Because these satellites going around the Earth are in a lighter gravitational field, less warping of space and time, and so they run a little fast. So if Einstein hadn't come up with it, and nobody else had observed some weird effect happening with particles that are going very fast, we see these all the time when high energy particles come smashing into the atmosphere from distant supernovae that blow up, they last longer than they should too. They make it all the way down to the surface of the Earth sometimes. So someone would have seen it and gone, hey, there's something happening strange here. But if not, once they came out with the GPS system, they would have invented general relativity. That's the equations of it, and had to figure that out. So he spent time trying to unify more, come up with a theory, an equation that links electromagnetism and general relativity. You want to take electromagnetic force and gravity, put them into one, and make everybody happy. He didn't like the quantum world. He didn't like he made major contributions to the foundations of quantum physics. Really bugged him, all these strange things going on. And I'm going to show you some of the strange things in just a moment. So to kind of put it all together, and I covered all these different unifications in slides last month, but electricity and magnetism were seen as separate phenomena until electromagnetism was put together in the 1800s. So we figured out you move a wire through a magnetic field, you get electricity, and if you turn an electric field on and off, you get magnetic fields. So they play off each other, and we now have equations for that. Inside of the atom, with the weak nuclear force that helps the phenomenon of radioactivity happen, we've unified, we figured that out in the 60s, we unified that with electromagnetism in the 70s. So we have the electro-weak interaction equation. So that's nice. When it comes to protons, neutrons, and things in the core of the atom, it takes a strong interaction to keep those things together. And we're trying to put that together and kind of got some good headway made, but the standard model of quantum mechanics, kind of set down in the 70s, at least gives that a place to work. It's not completely unified yet, but we're working hard on that. That's another thing that the accelerators are working on around the Earth. Gravity, very different little creature. Of course, we have universal gravity, space-time geometry, put together in Einstein's general relativity in the early 1900s. Putting these all together in the end is the theory of everything we're trying to get. So, looking at the things we don't know is, what are the particles that carry gravity around? Well, light is photons, and we have blue ones inside the nucleus of an atom that help make protons and those neutrons and occurs like that. We have W and Z bosons. I won't get into any of that detail for the weak force. We have photons for light, but we don't have this linking between strong and everything else, and we don't have the linking of everything else with gravity yet. So there's still some big unknowns. There's plenty of job opportunities out there if you're a nuclear physicist or an astronomer. All right, so is that it? We just have these problems to deal with, and we're done? No, there's a lot more out there. One of the things that we're going to have to deal with at some point is that gravity is fantastically weak. 1 followed by 40 zeros, weaker than the strong force. And I showed last time that if you take a little teeny magnet off your refrigerator and pick up a paper clip, you're not amazed. But you should be, because this little teeny magnet, electromagnetism, is battling the entire Earth below you, an entire planet. It has no say in picking up a paper clip. So that's how much more powerful everything else is. And when you try to just force quantum mechanics and general relativity together, bad things happen. You get things that go to zero when you don't want them to. You get infinities. When you do different parts of the calculations and compare them, you don't get the same answer. It's just a mess. So with general relativity, we can take a look at the large-scale structure of the universe and explain things pretty well. We can go back close to the beginning of the universe. This is the baby picture of the universe. We'll be bringing this up again tonight. But this is just the slightly warmer, slightly colder points in the universe at the point where the universe became transparent. Went from Big Bang, kind of negative, very highly compressed stuff, expanded for about 380,000 years. Hydrogen began to form when it cooled down enough. And just like the surface of the sun, you can't see into the sun, but you can see a surface and you can see around the sun. There is a point back in time where the universe is just too hot for light to travel freely. So this is the last flash of the Big Bang, and the light can then travel through space to your eyes or to our telescopes, really, because it's microwave radiation.
There's only 380,000 years ago?
380,000 years since the beginning. So it's after the Big Bang. That's about 13.75 billion years back in time. So, quick history of the whole universe is flash, very dense universe, expanding extraordinarily fast. At some point it cools to where light can travel freely. You got a period of darkness where you have a lot of gas and nothing happened, but the first stars start to form. And we're looking for those right now. We're trying to probe back into this era. And then galaxies start to get together pretty quickly, quicker than we thought. With evidence that black holes also got together pretty quickly. And then the universe expanded, and then started to speed up. More recently, here began to expand faster and faster. And then quantum mechanics, extraordinarily successful theory. I mean, all the electronics around us are based on quantum mechanics, and it even made predictions of particles we hadn't observed yet as they went. And we go look for them and found them at or very close to the correct energies. So that's why we're looking for the Higgs boson. That's one missing. So once you get back to this early part of the universe when it's down close to the size of an atom or so, quantum mechanics matters again for the whole universe. And we don't have a theory for that. We don't have a way to handle space smashed up and energy smashed up that small and that high like that. So we spoke briefly about string theory last time, that the first big theory of everything that we're fighting with, and the one that we've probably put most of the money in, most of the researchers have spent hunks of their lives working on, is string theory, or superstring theory. And the whole idea is, if you haven't heard of it, is that down below the fundamental particles, so if you get down inside an electron or inside a quark, which 3 quarks make up a proton and a neutron, the particles that don't break apart anymore, at a fantastically smaller scale, are little vibrating strings of energy, little warped dimensions of space. And how they vibrate, kind of like the strings of a guitar or a violin. I play violin and viola, so I think that instrument all the time. But how they do it is, what we see is the particle with the properties that it has. So that's the quickest way I can cover string theory. It uses these little mathematical creations, kind of like Mobius strips in higher dimensions, to wrap up higher dimensions than the 3 that you're used to and plus 1 of time. And you get about 10 dimensions needed for these equations to behave properly. And now, instead of weird zeros and infinities happening when you put quantum mechanics and relativity together, you get a much calmer, quieter space-time down in there. So it seems nice. The problem is there are something like 10 to the 500 possible solutions, or even more. So we don't have a way to pick the one version of geometry that makes our universe. But neat things do happen. Instead of point particles meeting violent little impacts, you get calm mergings of strings. Pretty quickly, we have about 5 major theories of string theory that all, some had open loops, some had closed loops. The math was a little different on all of them. And people were then afraid, not only do we have lots of solutions in each one of these, we have 5 whole different avenues to go down. And someone came along and unified and said, hey, add one more dimension. They all are aspects of the same idea. So that's M theory. And it's at least kept people from despairing too much. These additional universes, dimensions allow, and size of the universe allow parallel universes, so we talked briefly about those. If the universe is really big or really flat, at some distance, 10 to the 10 to the 122 meters away from you, there's another one of you sitting in a chair listening to me talk right now. Because within our bubble of the universe, there's only so many ways you can rearrange everything. And out of that distance, which is an extraordinarily large number, you run out of combinations. It has to start over again. So in a big, flat, infinite universe, you get that. Another parallel universe that comes out of all this reasoning and quantum mechanics itself is this one, where every time something can be decided, you get all those decisions happening in a parallel universe. Every single possibility does happen. So I have a little expansion here. I talked a little bit about how weird the quantum world is, but I need that for later tonight. So let's hop into some new material from last week's stuff and talk about how strange this world is that you're made of. And every chair, and every bit of the floor, and planet and star around you. Well, down here, any questions at this time before I? Down when you get dealing with electrons and photons, we find that depending on how you look at a particle, the observation that you make, you can observe it as a wave or observe it as a particle. and they are both at the same time. Our intuition says you can't have two completely different natures like this, but that's the way it works. So another way of thinking about E equals mc squared, energy versus matter, like that, particles and waves. So if you just think about it this way, if you throw an electron at a wall, or a ball at a wall, it's going to bounce off, right? That would be the particle way for an electron or a photon to work. But really, it can also act like a wave. So as it approaches, this is the probability of where this thing actually is. As it comes up against the wall, in the middle, ready to bounce, it has a little foot all the way through the wall. So you have some percent chance, and this is 100%, there's a little maybe 10% chance in there, that it'll pop through the wall and keep on going. Completely normal behavior down in the quantum mechanical world. And I said last time, quantum mechanics just means stuff that's very tiny. You're down the scale of an atom and smaller. Well, molecules bigger. Yeah, we're getting bigger. But it's very obvious you're on the scale of an atom and smaller. So if you put a light bulb on one side of a screen and put a screen, pull a wall, put a screen on the other side, what would you expect? You got a light bulb, you got a wall with a slit in it, you got a screen on the other side, what are you going to see? A slit of light, okay. All right, you'd expect the light to go through and make a spot. All right. That's not what actually happens. Light will act like a wave and come through and actually make a bright spot here and then some slighter, dimmer spots off to the side. But it's not acting purely as a bunch of BBs or balls coming through the slit. Doesn't bother us too much. We can make projectors and things. All these little side bits of energy don't matter. But with light acting like a wave, if you put two slits in the wall, everything changes. So now you have the flashlight, two slits in the wall, what are you going to have? Turn on the light? Not two spots. You get a bright spot behind the center wall, and spots going off and off and off, getting dimmer as you go. Very strange. We had to do this in physics lab as an undergraduate, so it's really easy experiment to perform. You just build diffraction grating and a laser pointer and have some fun. And what's happening is the waves come through, light's now acting like a wave instead of particles, and these waves are interfering with each other. We have two crests, they add and make a bright spot. We have two troughs, they add and make a dark area. And it's similar to waves coming through a breaker offshore towards the seashore. All right, now let's get weird. We're going to go back to our parallel universe here. What if I just let a photon or an electron go towards these two slits, one at a time, and only release one a week? We're going to get two spots, or we're going to get the interference pattern?
Interference pattern.
Yeah, interference pattern. Week 1, week 2, week 3. Actually, we're doing more than one particle, but the pattern still happens. Now, you can't take an electron and cut it in pieces and put it through both slits. An electron is an electron. It's got a fixed mass, a fixed charge, spin. It just has those properties. But it seems to go through both at the same time anyways. Wave-particle duality. Really weird stuff. Yes?
So, I don't understand. Are you saying that waves and particles act the same?
They don't act the same, but how you look at them gives you the effect that you get. So here we're just letting them go through.
So it's a perceptual thing. Is that what
Well,
you're saying?
this is going to be a photographic film.
Oh.
So it's being recorded by something other than a person's eyes or perception. Yeah, you're right. You're getting it. You're getting how weird it is. That's the idea. Well, let's get weirder. Let's see how really weird this goes. And next year sometime I plan to do like a one-night quantum physics for dummies talk. So I won't call it that, I'll probably get sued. But that type of thing. So we'll get a little further, take some more time on these ideas. But if you put the light through two slits, you get the wave pattern, or this interference pattern. If you got particles, you just expect that, and what we see is wave. Unless I put some little sensor here. If I put a little sensor there and say, yes, the photon came through this side, or no, it didn't this time, then the pattern goes away. Then I just get the particle result. I've now made an observation, and I've changed what happens on the screen in the background. So keep that in mind.
So does that make it a quantum theory then, what you just said?
This is the portion of quantum theory where you're talking about wave and particles being the same critters at the same time. Right. So that's not all. There's a lot more weird stuff than that. So, another question? No. All right, so one way that the math works in the quantum world is to look at all the ways that these particles can go through the two slits. And in our parallel universe idea, you're saying there is, well, the dice roll, or the photons and the electrons head for the slits, and the universe is peeled off where all those possibilities are happening. Going through the right, it's going through the left, it's hitting the wall, it's going around the experiment and getting the thing that way. You add them all up, and mathematically you get beautiful solutions, because lots of things cancel each other out, and you get a nice way to mathematically handle this. Richard Feynman came up with this idea. So you have all these various paths that can go through the two slits, and you add them up, and you get a mathematical solution that equals what you get on a photographic plate. In our parallel universe idea, what's happening is all these possibilities are now splitting off, and everything that can happen is happening in those two universes. And in a way, you're getting like cross-universe interference. And we'll get back to that. So. Now, what we're interested in, we're talking about strings, and we're talking about figuring out whether string theory works, is we're dealing with stuff down at what's called a Planck scale. This is 10 to the minus 35 meters. It's extremely tiny, and the time it takes light to go across that distance is 10 to the minus 44 seconds, which is a really short period of time. This is so small that I guess the analogy is if you had an oak tree sitting on the earth, 10 to the minus 35 meters, where the string theory string size would be, that'd be an oak tree compared to the size of the whole universe. So, in your laboratory, meaning the whole universe. So it's extremely tiny, and it takes more and more energy to take a look down at that scale. And actually, that's the, if you could get photons to punch at that scale, to begin to probe it, you would reach the point where each individual photon would become a black hole, for instance, and pop out of it. So it is the ultimate limit. We can't go any further. And in fact, even if we could build a large hadron collider that went around the whole galaxy, we still would not be getting close to punching down to this region at all. All right, so some of the problems that we're going to keep in mind as we now go into the new stuff is we can't measure things at the string Planck scale. String theory doesn't seem to create its own space or time. String theory assumes that space and time are smooth and not broken up into little Planck scale size chunks. String theory assumes time is smooth and not broken into 10 to the minus 44 second little increments or frames. So we have some of those problems that may or may not be addressed by string theory as it continues to grow and go. And we have other problems like, just recently we found out that the universe is, the top there is present, largely unknown to us. What you're made of and everything that you're used to seeing with and naming are made of atoms, and that's about 4.6% of the mass of the universe. Dark matter, which I talked about more last time, is some particle that doesn't interact with electromagnetism, that actually outweighs galaxies like 10 times, like ours, and changes how they rotate and how gravity acts. That's a quarter of the universe. And dark energy, this expansion, this acceleration of the expansion of the universe that turned on about 7 billion years ago, it accounts for 72% of the energy mass weight of the universe. And we don't have holes in our standard model for dark matter particles, though we think they interact through the weak force, we hope, the way to detect them. And dark energy is really on the edge of what we're looking at right now. So
there's no dark energy at the Big Bang?
No. At the Big Bang, the universe is dominated by dark matter. Now, you did have, right after 10 to the minus 35 seconds from the beginning, you had inflation happen. And we made up a particle called the inflaton, the inflation field, that enormously expanded the size of the universe in an extraordinarily small period of time. Distant parts of the universe are moving apart vastly faster than the speed of light. And that's empty space, which is okay. Matter can't go faster than the speed of light. But empty space sure can increase that fast and make things look like they're moving apart that fast. So that we think is actually a conversion from gravity, like borrowing from the gravity's bank and pumping that into a superinflation period. But we don't yet call that the same entity as dark energy is today. Might turn out to be, but we're not there.
No question about that.
Yes?
John, did you say that dark energy emerged 7 or 8 billion years ago? Is that what you said?
Yeah, dark energy began to really pick up in dominance about 7 billion years ago, so about halfway back in the universe. As we see, the universe was decelerating, and acceleration, the deceleration stops, and we're just going at a whole constant. And then after that, the acceleration starts to dominate. So, yeah.
So is it true that we haven't really seen or measured dark energy or dark matter in an instrument? It's just that the calculations that we calculate the mass of the universe and the energy of the universe, there's missing stuff. So we call that dark energy and dark matter.
You know, with dark matter, we can see it indirectly. We can look at galaxies that are fairly close, and we can see the light from more distant galaxies bending through space, because gravity, anything with gravity will bend space-time. And so we see it bending and lensing through that. So by the amount of warping and bending, and sometimes we even see the same galaxy or quasar coming around a galaxy on both sides, we can very accurately measure the amount of mass that's there. We can look at the light coming from that and go, that's not enough. We need 10 times more mass there than we can account for in dust and stars, like that. So we can do it that way. There's the bullet cluster of galaxies are two galaxies that have collided and passed through each other, and we can look at the lensing, and of course the material, gas and dust, will interact with each other, but the dark matter doesn't interact with normal matter in the same way, so it just passes right through. So we can see two massive regions of space that are empty beyond where the galaxies are still interacting with each other in the middle. So we have got lots of indirect measurements of dark matter and what it is and what it's doing. Dark energy we get by looking at distant supernovae and seeing how their intensity and light curve varies from what we'd expect at that distance. And it was completely unexpected. It was announced in 1998, and people were very sure that if we found any acceleration universe, it was going to be negative acceleration. It was going to be a deceleration. It was going to be slowing down, getting ready to collapse someday. And it came out the opposite. In fact, I guess a graduate student came to his advisor and said, the universe is accelerating. And I checked it a bunch of times. He goes, get back there and try it again. That's ridiculous. So he had to go do the math again. But a completely independent group was making similar measurements, and they came up with the same conclusions. So the universe is unsteady and accelerating. Its expansion rate is not just a constant. Eventually, we think that this acceleration universe will tear the universe apart. Well, in 2008, they said, no, it's not going to really go. It'll get whole parts of the universe apart. Eventually, the Milky Way galaxy will be alone with the other galaxies away or combined with us. But then in 2010, they said, no, maybe it's actually going to dominate again and tear everything apart. So we might have the Big Rip someday. So 60 million years before the Big Rip, the Milky Way is pulled apart by the expansion of space. Because what it is empty space becomes more empty space. It's not that there's anything actually reaching and pulling out. It's just whatever's empty becomes more emptiness. Where there is stuff, it holds together for a while. But 3 months before the Big Rip, the solar system breaks apart, away go the planets. 30 minutes before the Earth explodes, 10 to the minus 19 seconds before the Big Rip, atoms themselves are ripped apart. So we'll see if, look, we're going to continue to refine this acceleration and figure out what that is. All right, so good. Here's totally new stuff. Another theory of everything based on information. So we're going to play around with loop quantum gravity and take a quick look at biocentrism, which is a really small player out there. And then we'll see in the end whether we ever can come up with a theory of everything if somebody named Gold and someone named Turing are right. Any questions before I get going further? All right, so we're going to look at two things, information and entropy. Oh boy, I've heard that word, entropy, before. What I'm going to show you is that these seem to be two sides of the same coin, that we're going to go through 14, I'll number them here, ideal 1, I2, 2. 14 different aspects of nature and science that kind of illustrate this, and then we'll leap into the new stuff here. And to help you as we go, I'm going to put a blue eye for things that are more information based, and this little spirally thing that says entropy will continue to increase until enough dark energy is created to rip the universe as we know it to shreds. Have a nice day. So let's keep these two flagged here. So here's our only real equation for the night, the equation of entropy. S equals K log W. Ludwig Boltzmann figured this out, and it's actually on his rather large tombstone here. And what initially was trying to solve was talking about what energy in a motor is not available for work. So you put in a bunch of energy, out comes stuff that makes your car wheels turn and your XM radio work, and then some stuff goes out the tailpipe or out through the heat of the car engine itself, and that was called entropy, for lack of another word at the time. All right. And we have 3 laws of thermodynamics, and I'm not really going to talk about it. You probably heard that energy can't be created or destroyed. You also can't cool things down to absolute zero. But the one I'm interested in is that the universe is moving towards a downhill equilibrium. We are succumbing slowly to entropy. In fact, your body is always fighting entropy. It's repairing itself in all sorts of different ways. So you need to put more energy into the system. So like tonight I had spaghetti with Alfredo sauce and Italian sausage. It was very nice. And that is my input to allow me to do work to keep my body moving around up here. But some of this is wasted. I can't live off of all of it. If I stopped eating completely, what would happen to me? Yeah, eventually entropy wins and I fall over dead. So pretty bad. So entropy, another way to look at it though, is how ordered or disordered something is. So an egg is very ordered, very nice, pretty egg. If I just stand here without a slide and say, picture an egg, everybody in the room would have just about the same picture in their head. Eggs only come in certain ways like that. If you start to get a crack, or if you drop it off the table, now you've got a smashy mess, and you now have a high entropy situation. So this is low entropy, nice pristine egg, high entropy situation, all messed up. The amount of information it takes to describe an egg is very low, like I just showed you. The amount of information I'd have to give you if I wanted to describe this messed up egg is a lot. I'd have to be measuring and come up with a coordinate system and say this piece is this big and that big, it's got this jagged edge. I could write pages and pages of description on how messed up this egg is. So there's more information here and higher entropy. Another example of high entropy is little girl's room, and just about an hour later it looked like that. Maybe she didn't want to do her homework. But again, higher entropy, and if here I could say, well, all the records? Wow, what's a record? All the records are alphabetized over here. It'd take a long time to describe where all the records went. So, entropy, when you play with systems, tons of natural systems, you find out that bell curves come in to affect all over the place. From grades, people's heights, thank you very much. You can go to the gym, if you look at the scrape marks where people stick the little pins in, there's going to be a peak, most scraped one, and less scraping up to the lightweights and less scraping to the heavyweights. Just about everything comes in bell curves like this, which is frequently seen when we're mapping out systems with some amount of entropy. All right, let's take a look at information theory now. With information, a lot of the world around you has a lot of redundancy in it. So, if you think of language, you can go down the highway and tune into an AM station and hear lots of static and moments where it goes away, or your cell phone when it drops. You can probably still hear the conversation. You can still piece together what's being said because we have a lot of that built into our language. Zip code +4 is redundant. Internet protocols use duplex. The computer said, I sent you this, did you get that? I got this, oh yeah, I got that. And they produce errors that way. If you look at pictures, you can have lots of snow, or like this morning looking out the window into the fog, you can still see your neighbors' houses and cars. You knew what was there, even though a lot of the information was gone. So this also helps when we're trying to break codes, trying to figure out secret codes in military situations. And look at the rules of language and look for repeated things in there. So working in Bell Laboratories, Claude Shannon was given the task, redundancy is great, but we know we want to squeeze as much as we can through phone lines in the future. What is that maximum limit? So the way he approached it was saying, all right, well, what is information? It's little things that tell you something is this way or that. Like Paul Revere, we had red light and green light. It was 1 light or 2. But you can say 1 by land, 2 by sea, but you have 2 cases there. So you have 2 bits of information. With 2 lights, you could do red, 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 green, green, red, green, green. You get 4 cases here. You have 4 bits of information. For 3 lights, now you have red, 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 green, 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 all the way through. You have 8 possibilities of how the redcoats would have been coming. And on the backs of wild Martian horses is my favorite. So you found that when you have a question with so many possible outcomes, you can answer it with log n bits, so or letters. So you put in a number of letters in here, and you have, my goodness, an equation that looks very much like entropy. It's just about the same formulation. So, looking at computers, look how much you can do with 1s and 0s. All of Windows is just 1s and 0s. Your genetic code is 4 letters, G, C, A, and T. our language was really overloaded with 26 letters, so you get a vast number of words, but it's better than walking up to someone saying A, A, B, 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 A, A, B, B, A, B, 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 A, B. It would take a long time to do that. But the maximum amount of information you can get through is n log n, and entropy is k log w. I'm not going to go into the equations, I just want you to see how creepy similar these are. And both increase over time. As things become broken or messy, you're also taking more information to describe the system. All right, so now let's look at our 14 ideas where information and entropy come in. One is Einstein's barn and pole paradox. We're going to go back to special relativity here. Remember I said when I'm moving fast, I get skinnier in the direction that I'm going. So here we have a 20-meter pole and a 10-meter long barn. Can you ever fit a 20-meter pole into a 10-meter barn? I don't think so, but what if you got it going really fast? You got it going up close to the speed of light here. Now it is shrunk in the direction that we were moving to less than 9 meters. So that should fit just fine, right?
For a fraction of a nanosecond.
That's important. Keep that in mind. So people standing here looking at the barn, watching the pole come up, go, oh, no problem. All right, now let's, relativity-wise, let's hop on the pole and ride along with it. To us, it's 20 meters long because we're connected to it. And we see the barn coming, and it looks like it's approaching at us near the speed of light, and it's only 400 within the 3rd meters deep. We're worse off than we were before. So that's the paradox idea. Now, how do you resolve this? Who's right? I mean, will it fit or not? The whole idea comes down to information. Because if you're going to put people here and say, all right, the moment you see the barn door, pull just about to this barn door, you slam it, and the people in the back, you slam it when it's in, and see if we can slam the doors at the same time. The information about where this leading edge is, where the back edge is, can only get to the people in the barn at the speed of light. No faster. Information can't go any faster. So, we had to do this in physics too, and it was a nasty problem. But you just have to map the distance of time, or time distances it takes information to get to each person observing it, closing and opening the door, and you see that it's really all based on your point of view. The people standing over here in the grandstands can be completely satisfied that both doors closed at the same time because the light had to get to them too, from the pole and from the barn. And the people riding would say, no, first door closed and opened, and then once we were through, the back door closed and opened. It's all information, travel, time. But not really paradox. Right? Again, we talked about this in my little addition earlier, but the pattern that you get on the other side of the 2 slits is based on what you observe. If you don't have any information about which slit the photon went through, you get the pattern. If you have some information about which slit it went through, then you destroy the pattern. So information seems to dictate the outcome of this experiment. And I go, okay, well, like you said earlier, you're sticking something here. That's messing up the experiment. It's interfering with the photon or something. No, it's weirder than that. Because we have something called quantum erasure. You can make the choice later to observe it. Here's the researcher in the paper first put together, and basically you can decide after the light has gone through the 2 slits or one of the slits, whether you're going to observe it or not. And the pattern will happen or not based on your observation. It's, now you're getting into weird for my brain. So I'm downstream, and I decided, yes,
So
question.
is that known as quantum theory then?
This is part of quantum theory, yeah.
Yeah,
This is
okay.
part of quantum theory, yeah. A lot more, but yeah.
Yeah.
So, so it looks like I'm making a decision down here, and the photons are going, wait a second, you made an observation, let's go back in time a little bit and pick a slit to go through or not. What? How's that possible? And in paper, I think I was in Nature literature I read, they actually talked about an experiment where they make the measurement of between the slit in the screen, and they store it in a little computer box, a little computer memory stick, and whether they destroy that information in the little box or not dictates whether the pattern happens or not. So if you make it so you can never find out which slit it went through, even after the fact, then you get the pattern. If you don't, you don't. Yes?
Can I see that website again on the previous slide?
That one? Okay. So yeah, you can read all about that at grad.physics.sunnyysb.edu. I can bring that up at the end too. So this is again information. We have information changing the outcome of an experiment. Just an observation. Good?
Yep.
Okay. All right, another quantum mechanical weirdness is illustrated in Schrodinger's cat. Now, you can see there's a can of poison here. Schrodinger did not hate cats, so we're going to take a break in about 8 minutes here, so I'll get you your hour break. But the idea here is you've got a cat in a box, you've got poison, you've got a Geiger counter, you've got something that's a quantum mechanical system. You have uranium that's randomly giving off particles. If the particle happens to go in this direction and hit the sensor, ding, it sends out the poison and the cat dies. Now, if you seal this box up with oxygen, of course, I love cats. I've had cats for 40 years of my life. And you don't have any observations coming out of it, you cannot say whether the cat is alive or dead. You have coupled this cat with a quantum mechanical system, and the way one way of looking at what's happening in here is the cat is both alive and dead at the same time. In the first minute, the cat's mostly alive. After a few hours, the cat is probably mostly dead. And it's not until you open the lid and say, kitty, and get little kitty kisses, that you know whether that happened or not. Call this superposition, this is one way of looking at it, and the cat becomes in a state of bothness, alive and dead. It's probably a less violent illustration of this, but again, it's information. When you open the box, you get an observation. I think it's the Copenhagen interpretation of quantum physics that says what happens is the wave function collapses at that instant, and all the other probabilities go away because you've made an observation. Now the problem with this is that these possibilities do interact with the world. This box is not going to be completely soundproof, wiggle-proof, energy-proof, and everything. There is information coming through. So on the large scale, it's harder to see this stuff, or maybe impossible. But in the quantum world, down the size of atoms, this matters a lot all the time. All right, idea number 4 leads us to quantum computers. That we have, at least in theory, and in practice, in very simple versions of these, created computers where the ones and zeros are actually these little probability packets of waves of these particles. And they interact. And as long as you don't observe them, just like the cat in the box, they can be everything. They can be every possible state that the computer can be in all at the same time. So where the computer making the slide is going ones and zeros one at a time, or breaking apart, sending them through 2 processors one at a time, or whatever architecture is, it's one at a time. Ultimately, these are doing all the states at once. So you could crack codes that would take millions of years of the normal computer, theoretically in seconds. Because when you observe it in just the right way, you get the answer that you want. Now, how to make this work is really complex, but they're working on it. They're working on quantum computer components and building up the number of bits, quantum bits, qubits, that work at once. Once again, working with information. Another weird effect, and this is originally put down by Einstein and a couple other guys, was he said, you know, if you guys want to keep believing in this quantum physics craziness, then you can have 2 particles that share a common birth feature of some kind, you can move them across the universe from each other, and you could flip this one over, and the other one would flip the other direction. That's absolutely ridiculous. And he called it spooky action at a distance to make fun of it, and ultimately it turned out it's exactly how quantum physics works. And it's actually thought by some to be what helps reality itself hold itself together. That's too deep for me, but we've been able to do this. I think we're doing a lot of this over in Europe. We've been able to go like 100 miles apart with two particles and flip one and flip the other. And it sounds like a great way, and it's happening instantaneously. As we can tell, there's no travel time at all between this particle and this particle, seemingly to violate the speed of light, but information doesn't travel this way. So, you know, all your science fiction authors will go, we have an entanglement device that we use to keep contact with all the planets of the Federation. You can't get information to go through this. So we don't violate special general relativity with this, but it does happen. That's probably deep enough to go there. So with quantum entanglement, one of the ideas is that all particles are entangled from the moment of the Big Bang. They conclude most of reality is held together by this entanglement. Problems with that idea is that entropy is running things down. You have noise in the universe. You have interactions of all these particles, and what comes with that. So, all right, we will take a break now, and we'll get back to black holes and information, and figure out what the largest amount of information you can get into a memory stick could possibly be. So, stretch your legs, get some water. Scientists can get involved in the game.
We lost them to the football league.
I guess I did.
We need a door closer.
Oh, that's not good. Thank you for coming.
All right, ready to bring it on in?
Yes. Close the door.
Yeah.
Do we need to put the cooler back on, or is it okay?
Let's go
The
small,
temperature?
more to the
Cooler in here.
Okay, cool there.
Cooler?
Yes.
Back up.
I just moved around a lot, so.
It's your entropy.
It's my entropy. Yes, I have a lot of waste heat. All right, so we're about halfway through roughly on our little ideas here. We'll get to our next big theorem.
Hey, Johnny,
Yes.
don't forget, whoever asks the best question.
Whoever asks the best question, that's right, gets a free t-shirt.
Who judges what the best question is, though?
Yeah, I guess I do, yeah.
That's up to John.
So,
Just thought we might get a vote.
one researcher asked the question, you couldn't find their name, I read it actually in Scientific American magazine back in the 90s. What is the largest amount of information you can jam into a volume of space? And it makes sense, and you got these little memory sticks, and so if I fill this room with them, okay, great, I can make the little transistors and components to them smaller and smaller and smaller, they'll never even taking time here. You can start using individual molecules, but how much is the theoretical limit to what you can jam into space to get the ultimate memory stick? And out came the equations of a black hole, and what's even creepier is it's the surface area of the black hole, which turns out to be K log W. We'll talk about what that means in this case a little more. But again, it's the number of pieces of information you can jam in there. But it's not the volume. Like, if I ask how many water balls, well, is the largest number I can put in a little Thompson observatory, I picture stacking them on the floor to the ceiling. not just wrapping them around the walls and over the ceiling and over the floor, but when you get to this extreme, it's the surface area that determines the largest amount you can get in there. So,
Surface area is at the
event horizon. Yeah, we talked about black holes last time. Did a primer on on them last time. But the idea of black holes take a whole bunch of mass. Usually have a much larger star than ours, and when either it's death explosion jams the core downward, stronger than the atomic forces and electromagnetic forces can pull up, it falls into a black hole. Or if you just get too much mass in one place, then the gravity wins, and everything collapses down to a point, singularity in the center, and you have a point of no return around that singularity called the event horizon. And the event horizon is just the point where you have to then go at or faster than the speed of light to get away from the black hole. Now gravity increases as you get to a black hole, so time stops here, space compresses here too, and we'll talk about this in just a little bit, but if you're falling in a black hole and you just go in, you don't know when you pass the event horizon, you're just falling in towards the singularity. But time and space change roles at the event horizon. Time and space tip over, and now you could go anywhere in time you want that the black holes existed, but just like our future right now is 1 hour from now. We're all traveling an hour forward. There's nothing you can do about it. Your future in time is the center of the black hole, and there's nothing you can do about it. So time and space change roles, and it's really weird in there. Yes?
So is that the amount of information force on the mass then? Is the density the same in black holes?
Is the density the same? The event horizon size is based on its mass.
So the mass is proportional to the amount of information you have, is that right?
Correct, yes. Because what we're throwing into it, chairs or cars or SUVs or stars or planets, is all information, right? You're getting ahead of this. You're right. So, early on it was thought that entropy is disorder, right? What happens in a black hole? Everything is smashed onto a point in the middle. If I tell everybody here to picture a point, everybody gets the same point. But you're throwing stars and planets and galaxies into these things in some cases. Where is all that entropy going? Where's all that information going? Everything's in one little point. We've got every black hole with the same mass, is the same size. Boring. So, does this second law of thermodynamics fall apart in black holes? Another question is, does this quantum information get destroyed? Which is a violation of one of the laws of quantum theory, is that you can't destroy information. You can move it around, you can change it, but... So along comes Stephen Hawking. Here he is. He has Lou Gehrig's disease and he's in a wheelchair, pretty famous. He has a Universe show on TV. But he observed, I don't have the slide for it, but throughout all of space, in the emptiness here, between atoms, there are particles coming and going all the time, below where we can detect them. We can't pull them apart. They don't exist long enough, but they're particle and antiparticle that come and go, annihilate each other, and it's happening throughout all the universe. It's another way of looking at what happened with the creation of energy and matter in the beginning of the universe, that the expansion right after the instant of the Big Bang was so fast, these little particles were pulled apart and became real particles that weren't vanishing, able to reach each other again. But we can measure that in the lab by something called the Casimir effect. You put two plates very close together, and the little particles that are coming and going in the vacuum, the particles coming and going between the plates can only come and go in the opening between the plates and not in the direction of the plates. On the outside of the plates, the particles are coming and going in every possible orientation, so you get a little push inward on the plates. It's like vacuum becomes a little more sucky in between the two plates. That's a technical term. So Hawking looked at these little particles and said, right at the event horizon, these particles are coming and going all over the place. But if they happen right there, one particle will get away and the other falls in to the black hole. And by a little clever mathematics, he showed that this is negative energy and this is positive energy. So you feed negative energy in the black hole, you start to whittle it away. Remember, nothing escapes from a black hole, right? Well, this isn't over the event horizon. This is outside. This one will get away, but this one isn't. And so you get a release of energy, a release of information from the vicinity of the black hole. So all black holes actually have a temperature. It's extremely low for your average black hole, and even lower for the big galactic ones in this core of galaxies. This temperature doesn't matter right now because the whole universe, from the baby picture, about 2.7 degrees Kelvin, is a lot hotter than these black holes. They're about 0.000, I don't know if I had it up there, 0.0002 Kelvin or something. Very, very low thing. So every black hole in the universe right now is still getting more in from just the glow of the Big Bang than it's giving off. But someday in the future, as the universe keeps expanding and cooling, these things will start to evaporate. 10 to the 200 years out in the future, you'll start to see the smaller ones finally end, pop, and release the last of their energy. So the universe will light up 10 to 200 years from now by popping remains of black holes. And there'll be another bright age for a while. And then darkness will settle for good. So Hawking and this guy, Leonard Susskind, had a bet that whether information really was lost in there or not. Is this glow just the entropy leaking away, just the waste heat, or does information come out? And Hawking actually conceded, I think 10 years ago, 12 years ago, to Leonard Susskind and said, yes, I think the information does come out. It's really scrambled, but theoretically you could reconstruct every planet and car that fell into the black hole if you're some super technological civilization way off observing black holes for trillions and trillions of years. Not something we care about doing right now. And so he gave him the Encyclopedia of Baseball as the reward for winning that. So you can't store the information at the point. You can store the information at the surface. Where does that entropy go? One way to look at entropy is in gravity is that gravity kind of turns entropy around for a while. I mean, it seems to be settling into a nice point. It doesn't. We'll see that in just a second. But even here, I mean, if this was a big gas cloud floating around in the galaxy, and gravity pulled together, we eventually be a star. We got 8 planets and 4 little Pluto that we can call names, and some other Kuiper Belt objects, and we got mountains and plants and people, and for at least locally, at the expense of entropy creating tremendous amounts around us, we came to a less entropic state because gravity pulled things together. So it's a little step back in there. So the question is point versus surface. This is back to the point of view. If you look at a particle, it's a wave, or it's a particle at the same time, electron or photon. If you are the one falling into the black hole, you go wee all the way down to the point in the middle, and you never even know when you fall past the event horizon. To the people out here, though, looking at you fall into the black hole, they see, because of time dilation and the way space acts at the event horizon, everything piling up and coming to a stop in time on the surface of the event horizon. So everything was right there at the surface of the event horizon, not falling in, from our point of view. And this is what, I think it was Susskind again, look at the picture. Susskind again, who showed this, is just, it looks like a paradox, but it's another duality. If you're the one falling in, you don't see a wall of energy that you have to punch your way through, which you can. Again, you get smashed onto. But for us, our point of view, you do. Yes?
What happens if the black hole's rotating?
It makes things a little more complex, but not fundamentally different. you get something called an ergosphere around it, which is a place where you can actually get work out of the black hole. So in the future, you'll have civilizations that will come up with ways to mine the energy of rotation out and power planetary civilizations or whatever. But I don't think it dramatically changes the underlying ideas here.
Then what's frame dragging about?
Frame dragging is another part of general relativity, that just like swirling your hand in the water in the bathtub, the water will eventually start to drag along with your hand. A rotating object will drag space with it. And so space and time are stuff in general relativity. They're not empty fluffiness and some sense of going forward in moments. They are stuff that is manipulated by the presence of energy, mass, and like that. Yes?
Now, I thought you said that if you go into the black hole, you could move back and forth through the time that's in the black hole, but you also said that if you go past the event horizon, you're just going right to the singularity and you're done.
Right.
So
I'm using the outside and inside view at the same time.
Okay.
In the outside of the view, you have no time left because you're at the event horizon, and your only future is down. From inside, you can move around and like that, but you realize there's this tug forward, and the tug forward is true to the singularity. So yeah, I'm just flipping. The things are interchangeable, so if you're in it or you're out of it, you see it one way or flipped. So, yeah.
You said these black holes eventually will pop. Was our Big Bang just a black hole, and our whole existence is one of many other Big Bangs too?
That's a great idea, and we'll even see a little bit later how you can kind of think of the universe as a black hole, because we have an event horizon around us. It's 47 billion light years in size, but it isn't really that way. With a black hole, space and time that are there are warped and twisted and dragging and doing all the things like that. But in the beginning of the universe, space and time were part of the mix. And so when a black hole pops, it's just a release of energy in an existing framework of space and time. At the Big Bang, you went from a singularity where all of everything, space and time, were also incorporated in with the energy. And so all of it expanded at once. So it is a different phenomenon.
But isn't there a theory that talks about when things get pulled into the singularity, that the other side of that could be a Big Bang?
That is that way, and that was an early theory that's disproven. It's the wormhole kind of idea.
Yeah.
From our point of view, there's no time to do it. Now, there are actual mathematical ways to create a baby universe. In fact, you could do it in this room. In fact, and all I would need would be probably about 50 paper clips worth of mass. But when I do the right stuff to pinch this out of our space-time and create a new Big Bang, what the math shows is you get singularity and you get a little event horizon. So as soon as you try to create a baby universe, it's hidden from you. So there's a censoring process built into general relativity that doesn't let you see what you made. So weird. But it doesn't happen with your random black hole, and it happens for doing it just right. Not a lot of energy though. Alright, so again, this weird duality comes out that the entropy and the energy eventually does come out of the black hole because it evaporates. So gravity can reverse entropy locally. I already talked about that. A way to see that is when the universe was created, it was very low entropy. Everything was very simple in a small volume. Everything spread out into higher entropy. Now, if you turn gravity on, everything spreads out and then forms stars and galaxies, black holes that eventually evaporate. If you have the universe expanding quickly, then after the black holes evaporate, everything just keeps spreading out further and further. So gravity again gives us a little break from the relentless march of entropy forward. Which kind of brings us to the idea about time, idea number 9, is that entropy, and again, this is not universally held. There's people who are very upset about thinking of entropy as being the thing that gives us the direction of time, but in a sense, it does. relativity and quantum mechanics, you can put a negative t, time, into the equations, and everything still seems to happen normally. I mean, the same time relations happen, particles come together, bounce like this, or they come together, bounce like that. Two particles decay into two particles, one particle decays into two particles, or two particles combine to make a particle forward and backward in time. Doesn't seem to matter. But entropy seems to be, in the way we're looking at it, what makes the past look different from the future. Gives you this sense of a flow of time. So the universe is very, yes, go ahead.
So could one of the curled up dimensions of the standard model be another time axis?
It's possible. I think they played with those ideas that you get like a fifth dimensional time and a fourth dimensional time. Best I can tell, everything that works and makes some things look like our real world, all those are curled up spatial dimensions. So there's only one time ticking dimension. So that's the best I know of off the top of my head. So how the universe get wound up to be so special, be back, have a beginning point different from now, and that possibility is just a very empty beginning. A quantum fluctuation, like a pile of paper clips that someone pinched out of the universe and created ours. Space inflates and fills the universe with borrowed gravitational energy that now looks like particles and energy that are basically the same thing. So entropy constantly increasing as we go off into the future. The secret is having a very specific low state in the beginning. If it was too messy, then we wouldn't be here. And if it was too boring, you wouldn't have any of those little fluctuations on the background radiation field that we saw. You wouldn't have galaxies and strings of galaxies and things coming together in the way that we see them now. So it seems very special, which brings us to why we're here. So we call that the anthropic principle, looking at all the incredible, not only a low entropy state, but all the different forces, how they interact with each other are just right for you and I to be here now, sitting and breathing and living and like that. It seems really special. So we have in the anthropic principle a couple ways of looking at this, two versions. One is called strong, one's called weak, but I'll just come one in a second. Our place in the universe happens to be fine-tuned for us to be here to see it. So this happens to be that way, so here we are. Second version kind of pushes it a little further, says the universe must be fine-tuned for life. I think, therefore, the world exists. So this very specific low entropy had to happen for us to be here right now, but others say this isn't a very scientific way to do it. We've got one universe and one race of thinking beings. That's not a lot to draw all these great conclusions from. But one of the people who worked with it did use this to predict that there was going to be a cosmological constant, which is dark energy, could be dark energy, similar to what we see now. Because there had to be something that kept everything from collapsing together too early. And then they discovered it, and so it did make a prediction, which is better than string theory has done so far. All right, so back to parallel universes for idea 11. We can draw a bubble around us, like an event horizon, that encompasses the whole universe. I call it the Hubble bubble. If I looked it up, and nobody else calls it that, so I like it.
Is that come inside the baseball card bag, or?
You can calculate how many states you can organize everything in, information-wise, and you come up to the same number that we had before for our parallel universes. 10 to the 10th, 122 meters away, you guys are doing this exactly. And also, this distance, everything is exactly the same, but I'm standing 1 foot over here instead. So it's bizarre. But all it is straight information calculation. So there's other U's out there based on that. So if the information inside of this bubble really can be described purely by the information on the surface, like a black hole, then according to Jacob Bernstein, not the volume, it's almost like we could be created as a hologram, a three-dimensional image from the two-dimensional surface all the way around the whole universe, where all the information that makes us actually is sitting. Okay, well, that sounds great, but how does that work? I mean, I feel pretty solid. I feel like a hologram, to me at least. If I push a chair or something, I can feel it too. Where would this be? I mean, does the light energy information travel from this bubble all the way through the universe to us? Right? That means the bubble is back in time someplace. So I have a graphic here. No, I don't have it here. I'm jumping ahead of myself. So sorry. So that bubble could be back in time, or could be someplace else, and we'll get to that in a second. So the universe, in this way, acts like the memory on a computer, the ultimate memory on a computer with bits and bytes, and we have, say, an infinite amount of information that can be stored on an infinite universe, but for us, it's a finite amount that would create us. So if we were a simulation, if it's just a big bubble around us that's projecting us somehow or being computed, what would it take to run the simulation? Well, let's say we turn the whole Earth into some mysterious stuff called computronium, and every little particle is part of the computer computing away. You might get 10 to the 33 to 10 to the 42 operations a second of an Earth-sized solid computer. Human brain's about 10 to the 17 operations a second. If you look at every human being since the beginning of human beings, assume they all lived 100 years, that's about 10 to the 35 operations. So it would take under 2 minutes to run the whole simulation of the human race on the slowest version of the Earth computer. And add dogs, cats, birds, and planetary motions and stuff, and you up it up to a few hours or a few months or something, but it's still something that with a pretty, cosmically speaking, modest computer, you could simulate everything pretty easily. So to sum up all these ideas, entropy lurks everywhere and information may be more fundamental than energy. The equation of everything kind of looks like SK log W. But does this really do what we wanted? We wanted to unify the forces and come up with one equation that did that. So can we get there? Yes, and this is our final idea, and our next theory of everything is loop quantum gravity. Loop quantum gravity says there are no higher dimensions. There's 3 of space, 1 of time. It creates space and time itself. Atoms of quanta in space-time, 10 to the minus 35 meters, 10 to the minus 44 seconds, are what make up everything. And you get rid of singularities. There's no more points in black holes, no more singularity at the Big Bang. The Big Bang actually becomes a big bounce. And this is how the diagrams work. You come up with these little networks, and I'm not going to get what the numbers mean like that, but they're spin networks, and as these map out, space and time come into existence. The interactions of information at these nodes and passing along are the forces as they click along. So you get loops, and when they intersect surfaces, they create space. What are these loops? These are network loops. They don't have a physical existence. They're mathematical tools that show what's happening to information. As these go along, space comes into existence as you go. In the early universe, you had so many things intersecting spaces, or slices, that you had incredible expansion of space-time. As the density lowered, then the Big Bang calmed down, and we went into a normal expansion phase. They kind of look like this in the mind's eye of those who work on the math of it. And these little loops are down there at the 10 to the minus 35 Planck scale size.
Would you back up that slide for just a moment?
Sure. Okay.
Yep.
So you get rid of problems like singularities in the Big Bang and singularities in a black hole. by saying there are finite chunks of space, and you can't cram energy or information about energy inside these any more than you can cram more memory into a memory stick than you can. So as you increase the energy of a photon, its wavelengths get shorter and shorter and shorter and shorter. When it gets down to the point that it's near this size, now the only points that are intersecting reality are at each edge of space piece. And so the wave you really get are these little dark dots here. Cram more energy in and you're still only getting this nice lazy wave here. The energy then goes elsewhere. It goes into inflation. It goes into field strength of the early universe or inside of a black hole. But you just can't cram it any further. You don't get jam space and time down any further because there are no smaller pieces of it.
It's like the aliasing you get when you time samples.
Yeah, it's the same idea as sample. Yeah, absolutely. So this baby picture of the universe happened after maybe a bounce. Everything came together. You got as much information and energy as you could pack into this area, and then it repulsed and out goes again. You get a bit different physics in the previous universe, maybe so. That's beyond what they can do with it right now. So particles come from energy. Energy comes from the negative pressure, positive energy density of the universe. Once the expansion happens, it happens so quickly that the virtual particles are pulled apart, or another way to say it is energy is pulled out of the gravitational field and converted into energy particles.
What about the antimatter quantity that was at the very bottom of that slide?
With the matter and antimatter quandary, they have hope that this will show why there is an asymmetry in those, why one is created over the other, and they haven't solved that problem yet, so it's still there. So inside of a black hole, you don't get a singularity. You just get the most densely packed loops that you can. So you probably have some kind of solid inside of a black hole. Maximum amount of energy compressed based on the space-time quanta. And then again, Hawking radiation allows it to evaporate. Once it's small enough, this explodes outward. We don't know what that mechanism looks like, but it's easier to get energy back out from space, looking at it as someone falling in, or off of the surface, looking at it as someone looking at a black hole far away, than it is to try to explain how it comes out of a point in the middle. So even John Wheeler, a physicist who lived in 2008, started to really lean towards information as being fundamental to reality over energy and matter and like that. And just, again, bringing back the idea of low entropy and low information content, be like a stack of coins all organized across your table, every head up on one side, or high entropy if you scatter them around. And if you just have 1,000 coins and mix them up on the floor, this is how many combinations you can get the coins into. And most of these you wouldn't be able to tell one from the other. So looking at black holes, the ultimate way to scramble coins on the surface, and what we find is that the entropy of a black hole is equal to 4 times the Planck scale. So it takes 4 little Planck distances to make a yes or no answer that bends the whole surface of the black hole. So the amount of hidden information is indistinguishable states of a system is one way of looking at entropy. The amount of information you can't easily get out or can't recover is another. The amount of information no longer able to do work, energy no longer able to do work, or the numerical measurement of uncertainty of an outcome. All these things here. So this takes us to the big discovery I just made sense of last month, reading Brian Greene's book, Hidden Realities, that this Hubble bubble, this holographic universe, rather than being some neat abstract idea, has come home to give us a really solid, interesting link. loop quantum gravity and string theory look like the same theory on two sides of the coin again. So the idea is, where does that information that makes this a hologram exist? Back in the past, out in distance, Juan Martin Maldacena, I guess, shook the physics world with this idea. About the year 2000, he linked two-dimensional string theory universe to a two-dimensional particle field universe. An idea called deep brain theory. And here, the volume universe inside is reflected completely on the surface surrounding it in a higher dimension. And there's no gravity on the surface, there is gravity on the inside. So depending on which one you're looking at, you can actually solve problems in string theory that were unsolvable by just hopping out onto the surface and doing the math here. Or things you can't solve on the surface, you can hop into the volume and solve. And so over the last 10 years, string theory has gone almost fully into this holographic universe idea. Superstrings on the inside, where we are, look like fields on the surface. A black hole on the inside looks like a field of hot radiation. No singularity, no event horizon at all on this two-dimensional surface, giving more credence to this idea that the information is not destroyed and there's a whole other picture going on here. And just like the previous theories going from Newton to Einstein, Einstein didn't destroy Newton's theory, he just added on to it, and this just adds on to existing string theory, quantum theory, and general relativity. All right, so do we have experiments? Yes, we need experiments to do this. Is space smooth or choppy? Well, we're looking for evidence that there's choppiness in space. One way to do it would be to see particles coming from distant explosions in the universe and see if the light smears out like a light goes through a prism and becomes a rainbow. We've seen some evidence of that in some observations and no evidence in later observations. So we need more things to explode across the universe to help us with that. All right, so that ends that theory of everything. Here's our final little look. We have one more, and this is biocentrism. Biocentrism is actually creation of a biologist and astronomer author. And if you have Astronomy Magazine, Bob Berman is a regular columnist in there. And what they did is said, all right, you guys are all excited about quantum weirdness and like that, the observation effect of light going through slits, but you're stopping down at the size of an atom or a molecule. Well, with the two-slit experiment, I didn't tell you this earlier, is that we can throw electrons at the slit, they act like waves. We have now thrown atoms, I think argon, atoms at the slit, and the atoms, whole atoms, are going through like waves. We've got small molecules through that at slits, and the molecules go through like waves. And their goal is eventually trying to get a virus to split through and ghostly go through two slits at once, but still be one virus. So there are experiments that are beginning to show that this weirdness actually extends up towards macro world here.
Cats?
Cats, right? We're not up to cats. I don't want to throw cats at slits either. It's horrible. So what they said is, actually, let's just throw it all away. Let's just take it to the extreme that reality itself is based on the observer. You need an observer to make anything come out and appear. So here's Schrodinger's cat again, and classical story of either alive or dead. The quantum story is it's both at the same time. They say, no, what happens is you get both possibilities, but the observer makes it appear. So, does a tree falling in a forest make sound? Yeah, if there's an observer. If there's not, then there's other mechanical things that you can later observe. It's the later observing that makes the tree eventually make a sound. Most extremely, once we observe, according to them, I'm not going to buy this, but according to them, once we observe the cosmic microwave background radiation, it came into existence from all the other possible ones that could have existed. More precisely, it came into existence to be the pattern that we needed for us to exist, to observe it, because we're here to observe it, and we needed that to be that way for us to observe it. So, all the other possibilities, there's actually a newspaper article that came out saying that astronomers are afraid that observing dark matter will collapse the universe. It was a real life thing. But that's the same thinking, that once you observe it, it's not going to do something. It can't just hang out there in a possible state. So they have 7 principles. We perceive reality as a process that involves our consciousness. Space and time are not absolute realities, but tools of human and animal mind. External and internal perceptions are intertwined. Behavior of subatomic particles and all particles are linked to an observer. Without consciousness, matter dwells in an indeterminate state. So there's nobody through here. There's nobody back in there. So what's actually happening in there? Right? Well, somebody walked through and got a tour, and you know the stairs and like that. But someone could have come in the back door and stolen something. Or maybe a fire has just broken out and something is starting to burn. You don't know. There's a bunch of probable states through that door that until I go, observation, everything's fine. Is there. And the universe is fine-tuned because we are here to observe it. Time doesn't have real existence outside of animal sense perception, and neither does space. So this is taking quantum mechanics to a real extreme. Maybe they're pointing out something important that we're missing, not putting consciousness into the observation. This may be further. It does not imply that you're creating all reality, because otherwise there would be 35 different versions of reality here. So there's something here that is constant. I mean, I actually wrote Bob Berman and asked him this question. He gave me an answer that's kind of weird. I said, how then do I open a book and find the same information that you wrote in it? If I'm observing this, I might observe something very different. Of course, if someone ripped out pages or substitute a different book in, that could happen. But as long as no tampering happened, and I'm thinking about his answer. I'm not sure I'm satisfied with it. So anyways, so going back to the anthropic principle, the universe is fine-tuned because we have the consciousness of it, and this takes us back to our ideas of quantum erasure and like that. Now, in a way, it's saying that the slit in the universe passed through at creation has now been determined now that we have observed it that way.
But couldn't we switch that around, say the universe created us, so it had something to pass information to?
They put consciousness at the tip. I mean, you could, but they didn't. They're saying consciousness is the foremost item, and everything flows out of observation. It bugs me, but yes.
Well, so it's easy for us to be conscious of what's in this room, and we can look around. You know, the universe is a big place. You know, that seems like a very big stretch. Maybe it was someone else was conscious 10 billion years ago or something. You know, it's.
Yeah, that's another thought. I put that in the email to Bob Berman. It's like, I couldn't find an email for Lanza. It's like, all right, what if we have aliens across the galaxy from us? Their observation bubble is coming towards us at the speed of light as our observation bubble is heading out. And so what happens if they did have totally different perceptions of everything? Can you have a consistent universe that way? So, but again, I'm not happy with their idea, their answer. So, my last concept of the night then is, if you guys can hang on, you still got enough in you to go a few more minutes? Okay. Last is, can we even have a theory? I mean, is it possible, or are we going down the rabbit hole with Alice, and we're just going to keep chasing this rabbit forever? Bertrand Russell was a mathematician who put down the principles of mathematics in 1903, and David Hilbert proposed that what we need to do is set down in a book all the axioms of mathematics. And we're going to go right back into this where we are at this moment. But axioms are the parts of mathematics that don't have, that one's stopped recording if someone wants to turn on. Yeah, okay. So mathematics, an axiom is a piece that can't be proven by itself. It's a building block. It's almost like a fundamental particle or a piece of information.
Assumed to be true.
It's assumed to be true. And, whoa, wrong button. I just observed it dark. And so his thought was all mathematics could be reduced to basic arithmetic, and we should formalize it, complete it, make it consistent, conservative, and decidable, and mathematics would be done. We could take these axioms, connect them to things we haven't yet discovered, but eventually we paint the whole picture of mathematics, and that's what he said had to be done soon. Kurt Gödel comes along, born in 1906, lived in 1978, Austrian logistician, mathematician, philosopher. He put out these two theorems in 1931, trying to work on this problem. And what he basically came up with was that any effectively generated theory capable of expressing elementary arithmetic cannot be both consistent and complete, which means there are true statements that are unprovable within arithmetic, which then leads you to conclude that there's not a finite number of these axioms, that you can create an infinite number of axioms. And how was that done? Well, he used prime numbers, and he mapped them to the axioms and theorems and showed logically true statements could be made in one system mapping to the other that could not be proven.
I'm sorry, this statement is false is one of my favorites.
Right. And that is what he did mathematically. He said, using the axioms of algebra, that this statement is false. All right, if you say that's false, and then you say, okay, well, that's true. If it's true, then it's false. That's false. But if it's false, then I'm going to go around a circle. All right. So if a mathematical system has that, then there's no limit to the number of axioms that can be built into it or make it up, is what he rigorously proved. I'm not going to do that. I saw one video of someone who actually gave a talk of all outer space just on that. He talked for an hour and a half, and it was deep. But the second theorem is similar. So any theorem, including the complexity equal arithmetical truths, so arithmetic is important here, multiplication, division, addition, and subtraction. The theory can only include a statement of its own consistency if and only if it's already inconsistent. So it can sound fine as long as it really isn't fine. So this is like me saying, John cannot say that this statement is false. I can't. I can say, oh, it's true. Oh, wait, no. Oh, wait. You guys out there can answer it for me, though, can't you? Yeah, you guys can, from your point of view, you can answer, John cannot say this statement is false. Can I or can I not? Yeah. So outside of the rules of arithmetic, you can answer these inconsistencies, but within the confines of it, you can't. All right, so how does this help us? Gödel's incompleteness points to this concept of I, or self-awareness and consciousness in a way. It takes us back kind of to the observer, because you have a system that's self-referencing itself. And if you want to read some good books on that, go to Hofstadter. Yes. Anything by him. Gödel, Escher, and Bach is one of the big classics, but he's written Gödel's Proof. He edited that, and he's got some other great books out there on that. So we have limitations on this. It's not true for just addition and subtraction. It has to have multiplication included in it to work. So we have looked and glimpsed at these theories of everything that use some of the hardest mathematics known to mankind. In fact, some of the thoughts on string theory are that we need to invent more mathematics just to get it to work. So it seems right now that the complexity of the universe is described by things much more complex than just addition, subtraction, multiplication, and division. So it seems that Gödel's theorem does point to there being no end. But if you can make the whole universe as just addition and subtraction, then there would be an end to this truth-seeking. So, is there a possible way that we could have math simpler than arithmetic that builds the universe? And one idea is cellular automata, and this is hot work on by many people, but the most famous recent worker came up with a big book on it, Stephen Wolfram. He came up with the idea of cellular automata. He comes up with really simple little rules that, like the game of life, just say, if the particle next to me is there and not there, and there's another particle, this particle goes away. If this particle, this particle, this particle exists, I will stay and add another particle here. Simple little rules, maybe 3 or 4 of them, and you get all this weird phenomena, weird patterns that over time create large amounts of complexity. So if the universe actually can work on simple computational rules, we may not be limited or unlimited by Gödel. So Alan Turing comes along now. He came up with the idea of the Turing machine, computational, early computational theory. He did lots of stuff like break the Enigma machine the Germans used during World War II. Wrote that code. But he came up with the halting problem, which is a very similar statement of Gödel's first theorem. And it says that you can't write a program that will look at any other program and say whether it will end or not, whether it will give you an answer or not. In a way, you look at the universe and say, there's no way to compute the future state of the universe without the universe doing it. So, the universe has to run forward. There's no way to model absolutely everything in there. So, from Turing here, we suppose the universe we live in is maybe a simulation, and being simulated by something that is a universal computer, like a Turing machine. What are these ramifications? All right, well, if it's based on algebra or arithmetic, then there are no ends to the things we'll keep discovering in theories of everything. Yes?
So maybe the answer is 42?
It might be 42. That's the next slide. No. Or if it's very simply based, then we may come to an end at some point in the future. If we're a simulation, then things we can look for would be software glitches. In the movie The Matrix, they played with that idea with deja vu. When they had that feeling of deja vu, that was a glitch or something that was being inserted or changed into the program. We could look for Easter eggs, and so you get the idea of searching for hidden messages from the thing that created the program embedded in pi or E. The infinite monkey theorem happens there. An infinite number of monkeys typing for an infinite time will create everything. Pi and E both have an infinite number of digits, so your entire DNA, everybody's DNA, is someplace in pi. It's an infinite number of digits, so every number describing every part of the universe is someplace in pi. The problem is finding it. But you have limitations on processing power. Maybe if you look at very fine scales in space and time, you might find granularity, or maybe things that couldn't be computed. Heisenberg uncertainty principle could be a manifestation of such a limitation in computation. But anyways, that's the ragged edge of speculation. So let's sum it all up here. String theory is the most researched and theory of everything out there. It addresses the largest number of questions, has a large number of people working on it, but it has lots of testability problems. It doesn't yet make concrete predictions that we can go out and work with. Loop quantum gravity creates its own space and time. Now seems to be linked to the concept of a holographic universe with string theory. Biocentrism is a big leap forward, saying that consciousness is a missing ingredient in everybody's work. And the computational universe is the idea that we might live in a calculated simulation based primarily on information. So maybe the most amazing thing is not if we can find a theory of everything, it's that the universe can be explained as much as it has already using the mathematics that we have. Or maybe it's just there because we're here. All right, so I got books you can read, and there's a lot of good sources here, and I can put those back up there. Other good places to get information, keep up with this. the Astronomy and Sky Telescope, Scientific American, Physics Today, Nature and Science magazines. Astronomy FM is a web station, puts lots of cutting-edge scientists on for interviews and like that, and so you can have fun with those. Questions, yes?
Is your slideshow available somewhere on the internet so I can review it?
Yeah, I think I'm going to put it, I have an education site where I have all my classes that I teach or put up, and I'll put one on that says public lectures.
What's the site?
Bikerjohn.com. Bikerjohn.com. I like to
Bikerjohn.com.
Yes, question.
I have a question on that Hubble bubble, but first, on pi, just because pi is infinite, does it necessarily mean that it has every combination of numbers?
We don't think it repeats. So because it's infinite, yeah, I think you're going to, because you have infinite, you have room for everything you have.
Okay. Now, in the Hubble bubble thing, as far as the universe is expanding. Sorry, this is the first lecture like this I've been to, so
oh, okay.
Pretty simple.
That's fine.
Is that basically saying the universe can never shrink? Because if earlier you said something else theorized that information can't go away once it's created, and if information is the event horizon or whatever of this Hubble bubble, therefore it could never shrink because all information is constantly being generated.
Right. By the acceleration of the universe, we don't think it will ever shrink. It's going to keep expanding until you've got one particle per billion cubic parsecs or something like that. But the information keeps increasing because you keep getting empty points, zeros, that fill everything.
Okay.
Other questions?
Put the slides back on the book.
Sure. I got these in chronological order. Hidden Reality, Parallel Universes, and the Deep Laws of Cosmos by Brian Greene is 2011. Grand Design by Stephen Hawking is good. Yeah, I got Brief History of Time up here. Once Before Time, The Whole Story of the Universe. Theories of Everything by Barrow. He's got a new version. This is the new theories. He updated it. The previous version is 10 years old. The Trouble with Physics, The Rise of String Theory and the Fall of Science by Lee Smolin. He works on quantum computers and information technology. And he's very bothered by a very complex thing that gets a lot of money that can't be proven. Warp Passages, Unveiling the Mysteries of the Universe, Hidden Dimensions by Lisa Randall, Fabric of the Cosmos by Brian Greene, Alien Universe by Brian Greene, New Kind of Science, Stephen Wolfram is a big book. 3 Worlds of Quantum Gravity, again by Lee Smolin, Universe in a Nutshell, Hawking, Gödel's Proof by Nagel, Newman, and Hofstadter, and Impossibility, The Limits of Science, and the Science of Limits is actually what I'm reading right now, and this is where I was working with Gödel's, because this is talking about all the things that are impossible in physics and science. So. Other questions? Yes?
Well, how do we know that the universe is made mostly of matter? Could there be other galaxies that are trying to antimatter, for example?
That's a good question. That is a remote possibility.
Repeat the question.
Okay, the question is, how do we know the whole universe is made of matter and not that there are whole galaxies out there that are antimatter? And there are currents of material that stream through clusters of galaxies and along strings of galaxies around the voids, the big empty spaces that make up the universe. And if any of these streams interacted, of normal matter, interacted with an antimatter galaxy, you'd have a halo of gamma radiation of a very specific signature. So we would see those as gamma ray sources that we don't. So observationally, we don't see support of pockets of antimatter. Yes?
Is the clumpiness in the cosmic microwave background related to the distribution of galaxies?
Yes, it is. Yeah, and it's related to quantum fluctuations when the universe is tiny, very tiny. So going from quantum theory up to those fluctuations up to the distribution of matter in the universe are one continuous story. Yes?
What's going on with the Large Hadron Collider now?
Right now, they did an extension of the first phase phase of the operation at a sort of medium energy, trying to beat everybody else to finding the Higgs particle. I think it's going to be turned off in January at some point and reconfigured for the next big power up. And there may be a phase in there, scratching the edge of my memory now, but there may be a phase in there that they're going to use like larger atoms for a little while, gold or something like that, and do some heavier components. And you accelerate. Energy is mass or energy, so you can either accelerate something really greatly, or you can accelerate something massive a lot, but not as much, and you can get as much or sometimes a little bit more of a bang.
So they had any collisions that might reveal the Higgs?
There's a story leaked out that they were starting to see a signal at one of the expected regions, but as they took more data, that went away. And so it should actually get stronger as they take more data. So anytime you roll dice or a coin, it's possible you get 30 heads in a row or 30 ones in a row, snake eyes. And that seems to be what that happened. They're getting random events on these collisions, and you just had a spurious signal for a while, and it's going away. So no, right now they don't see, I haven't heard anything credible about the Higgs showing up. Yes?
I think Stephen Hawking thinks it's possible to go backwards in time. What do you think?
I read Gödel first. The next one, I went back 2 chapters, and this is called Deep Limits, Paradoxes, Time Travel is a Universe Safe for Historians. So I don't have the hottest latest on this. Yeah, there are mathematical ways to do it. It seems that once you really start to bring in secondary effects, playing around with space and time at that extreme level, you start getting problems with that cosmic censorship and event horizon forms, or you get a colossal amount of energy that would cook everything that's in place. Like there's a legitimate solution to black holes that I think if you get them spinning fast enough and you dump a ton of charge into them, you can open up like a wormhole into a twisted version of space-time, and you could theoretically go in there. When you do the full calculations, right at the edge as you enter, energy approaches infinity. So you cut everything that tries to pass through. So you may get a glimpse, and then you're
so it doesn't look good.
It doesn't look good by what I know. There's a number of popularization books out there like that. So.
You can see back in time, though, if you can go faster than light.
Yes.
And then look back. Or if you could somehow circumvent that one rule, but you can theoretically see back in time.
Yes, question mark.
John, it seems like I heard somewhere there was some potential observations of, I don't know if it's information or a physical manifestation of something before the Big Bang.
Yes.
What was that, or what is that?
There is actually a number of different ways that you can have a pre-state of the universe before the Big Bang. You can have a big crunch that then bounces back out like I had up there. It seems right now that you get sort of a reset of everything at maximum compression. And so you lose the ability to read the information that's coming through. It's coming through, but it's coming through completely scrambled. And so you have, in essence, a very high entropy state being converted to a very low entropy state, and you lose the ability to read through that. So going by that, we don't think we could see it. In fact, we even think laws of physics could be different in the previous universe, and might even make it so you couldn't even get an electromagnetic observation through from it. We talked about last month, but with brane theory and string theory, once the universe gets really spread out due to the dark energy, and may allow a parallel universe separated from us by a higher dimension to drift in and touch the whole universe at every single point simultaneously, releasing a colossal amount of energy, and then you get a bang at that point. It would look and act just like the Big Bang, but you have no point. You have an infinite universe, and instantly becomes filled with energy and matter again that expands until it cools in galaxies and like that. You have a repeated banging cycle like that.
What do you know about that anomaly in the W map at the South Pole? There's that elliptical spot that is said to be an inconsistency.
In the background radiation?
Yeah.
Well, there's high speculation, but in the bubble universe that I showed you with other universes around us, you could actually have bubbles formed in a universe that inflates very quickly. You could have our universe very, very large, very flat, but surrounded by a region that still has inflation going on. And beyond that would be another bubble that's a whole other universe, possibly with totally different physics. And if these two bubbles got close enough that they touched early on, then you would see the interaction between universes in the cosmic microwave background radiation. And we don't think that that's what the signature is, because if that universe had a lower value for dark energy, it would actually tear through us like a tornado through wet tissue paper. So we would have a wave of destruction coming through the universe, and we're dead already.
So what do we think that is?
I don't know what mainstream actually thinks about it. I know that that's one more edge theory. Yeah, but that I don't know. Could just be statistical anomaly.
No, they actually think it can be.
It can be, okay.
Yeah.
I'll have to look into that more. All right, you guys out? Got stuff to show them?
Yeah, the football game is over, so the lights are out.
All right.
And I think the clouds are gone, so I think it is clear.
Go for it,
I think
people.
we can certainly do that. Thank you, John.
Thanks.